Our previous videos assumed a Poisson distribution for arrival and an exponential distribution for the amount of time to provide a service to the individuals. But what if we have a single server model with a finite population? So the previous models, when they had that Poisson distribution, what they really assumed is that the potential customer pool was so large that customers would continue to flow in at the same rate for every minute. But if you have a finite population, so for example, if you're a small company and you are doing the repairs within that company, at some point you are repairing something for everyone, and there's really no one else to pull from, no one else to enter into the queue. So you can think about this if you're the IT department and you are updating people's computers, right? At some point, everybody is in the queue or they've been serviced. There's no one else to join. So with the finite population and the single server, the fact that the population is finite actually changes some of our calculations. And so we'll just very briefly look at these situations so you can see how it changes in case this is your situation. So the formulas get amended when we have a finite population. We're looking at those same we're looking at those same measures in terms of those operating characteristics. We're looking at the probability the system is idle, the average number of units in the queue, the average number of units in the system, and the average time spent in the queue waiting. And so here you can see that probability the system is idle. We're back to the one server system, so you'll notice there's no K's in these formulas. But we do have that summation at the bottom because there is a finite number of n, that is the number of people in the company as we're going through using end. Everybody's been serviced or is in the queue itself. So you can see as we go from little n equals 0 to big N, that's that finite population. The average number of units in the queue is going to be dependent on the size of the population. That's that big N. And so it then is going to depend on what the probability the system is idle, as well as the number of people that are in that total population. Because again, once you have serviced them, then they're no longer in the queue and they're not being added to the queue. Average number of units in the system is going to be dependent on the average number of units that are in the queue, plus of course the being served. And so the time being served is going to be dependent on the fact that the system is not idle. The average time spent in the queue waiting is going to be a function of the average number of units in the queue, as well as the average number of units in the system, and minus the population minus those who are in the system, because those are the ones remaining, right? So the other measures for the metrics, the average time spent in the system, that average time in the system is waiting plus getting served. So of course it's going to be dependent on the average time spent in the queue. The probability that a unit has to wait for service is going to depend on whether or not there's anybody in the queue. So we have the probability the system is idle. And so the probability that you have to wait is 1 minus the probability it's idle. The probability that a certain number of units are in the system is going to be dependent on how many people are in the population versus how many you're looking for in the system. So if we, for example, were to suppose that your company services ambulances, you have 10 municipalities that are your customers, so your population is finite, then capital N is 10. And we could assume maybe the arrival rate for ambulances in need of service is 1 municipality per week. The service rate is 2 municipalities per week. We could do these calculations for that particular data set. To do that, we are using drstephpowers.github.io/BIA. We are under the simulation tab here. And in our Python workbook, let's go in here. We are looking at a finite population. We're importing pandas as PD. We're importing math so that we can do those factorial parts of those formulas. And so we really need to create the functions for single serve, for the finite population and the single serve probability for the finite population. We're going through these videos not necessarily because you are in a position where you have queuing. Maybe you do. Maybe you have a business where you're trying to decide how many servers and you're looking at the wait list or the call times for your service desk. Maybe you're Alberta Health Services. And we're calling nurses and we're looking at how many nurses are available and how long the wait is. Or maybe your Apple customer service, right? You would use these calculations. But even if you don't have an organization where you're using the queuing theory, the same approach we're taking here, we're creating our formulas, our metrics to see how we're doing. And we are putting that into a function so that we can then test as we change the different variables what happens. We can do those simulations to help us make decisions. So the general process here is to create a function made up of a bunch of formulas to help you as you do some simulations to make your decisions. And if those decisions happen to be to decide how many people are in the queue and what you should do about it, then we already have the formulas for you. So for our single serve with a finite population, we have our formulas here. You can see that math.factorial, that's the n with the exclamation mark after it in our formulas. And because our formula here has, we just go back, you can see that it has this sum from n equals 0 to capital N. What we're using to do that summation is we're actually creating a loop. And so what we're going to do is we're going to sum for x in a range 0 to, and we want to include n. So remember, ranges go up to but not including. So we want to make sure we capture it by doing n plus 1, not just capital N, because we want to include n. And so then we have lambda over mu to the power of x. So that's what this part of the formula is. And then the math.factorial is for those exclamation marks in the formula. So define your formulas, your metrics, put it into a function. And this function is going to be a function of lambda, mu, and capital N being the size of our finite population. We can also do the single serve probability. That's always the last one of these metrics we've been looking at here. It says, what's the probability of a certain number of units in the system? Our number of units is going to go from 0 to 10 because that's everybody. And so we can run through that list and see what the probability is. So here we're going to create the function, start with an empty list, number probability equals, and then hard brackets. Our loop, as we loop through, we append the value for n, which is I here in our loop, and then the probability with it. So we could look at this scenario. Our scenario here is that we have 10 municipalities that we service, and lambda is going to be the arrival rate. And so in this time, what we're doing is our arrival rate is 1 municipality per week. So the time period now is 1 week. The service rate is 2 municipalities per week. So here we have mu equals 2, and our n can go anywhere from 0 to 10. We will call our single serve for our finite model, giving it the lambda, mu, and capital N. And then what we can do is we can have those values in our dictionary here. So variable and value, probability idle, average unit queue, pull this information, and then we output it so we can see it as a report. So the probability that it's idle is super small. Notice that it's times 10 to the negative 0.05, which means that there's a bunch of zeros before that 3. The average units in the queue is going to be 7. The average units in the system is 8. And so because we have a lot of municipalities in the queue, we're not idle ever. The average time in the queue is 3.5 weeks. The average time in the system is 4 weeks. And the probability you're waiting is 99,999. So it's pretty much guaranteed that if you need your ambulances serviced, you're going to be waiting. Okay. So that's our single serve model with the finite population. So you can see the impact the finite population has on the system. We could look at what's the probability. We have a certain number of people in the system, and we want to run through the 0 through 10 group. So we call our function single serve prob underscore fin. And so you can see here that the most common number in the queue is actually that there's 9 people or 9 people in the system. So QN being serviced. So notice that it's on the high end. That very rarely, if ever, are there only 1 or 2 people in the queue. We're really having a hard time keeping up. The list is long. So anytime you need your ambulances serviced, you are joining a long list. And we know that the average wait time is 3.5 weeks. Okay, so you can use this type of information if you can collect a key couple variables, lambda, mu, and in this case, the finite size of the population, we can get a lot of information to help us make decisions for our organization.